good afternoon from the University Belgium. I want to present something about the structure interaction of dry wiring by covering OpenFOAM models of lubricant and the wire. My supervisors are typically and this week. Okay, so what's dry wiring? Actually, dry wiring is actually a wire that is going through a die in order to reduce the wire's diameter. The wire speeds can go from 1 to 2 seconds, and we call dry wire lubrication because the dye itself is not submerged in a lubricant, but the lubrication is done by circular values, the additives which are in trails, by the wire, and the light and the liquefied material. Why we do lubrication, of course, first of all, to reduce friction between wire and die, to reduce heat generation and energy consumption, and reduce wear of the die and extends surface life. Right. What this investigation goes about? So it's the purpose to develop a fast 2D axisymmetric fluid structure interaction simulation of dry wiring with subfield and wire information, and to enable parameter study to reduce its function. Right. That's this presentation goes about. Actually, this presentation will present a 2D axisymmetric FSI simulation of dry wiring with a classic information of with the aim to achieve a 10% cross-section reduction of the wire. With a sliding interface. Why a sliding interface? Because the wire is moving in axial direction, while the soap itself stays fixed in axial direction. Currently, the soap is approached as an Newtonian fluids that is thermal flow, and this simulation presents the first transient simulation, and after a while, its purpose to achieve a steady state. All right. So we have here the structure interaction. So what does that mean? Actually, between three components of it. So a fluid solver, a structural solver, and solving component. The fluid solver is solved as pendulum film, so a compressible isothermal solved pendulum film with an arbitrary Lagrangian and Lagrangian formulation, and is calculated in multiple ways. The structural solver is a Lagrangian solver developed by Höhn, and runs in the flow extended working model. To couple both solvers, a code called coconut, code for numerical tools, is used. Actually, a Python-based in host of the source code, which makes use of strongly coupled partition approach with quasi-union tools. All right, how does it work? So the fluid solver takes the loads, so pressure and traction, and going to give its data to the solver wrapper, which is included in components. This solver wrapper going to transport the loads to the solver wrapper or focus important one. With an interpolation in between, because the mesh of the fluid solver or the fluid domain and the mesh of the circular domain are not each other. And these loads are imposed by the solver wrapper for extent of the structure. So what does the structure do? It calculates radial displacement and axial velocity, or actually displacements and velocity. However, we just need the radial displacement and axial velocity to be imposed on the fluids. So due to the fact that we have the sliding FSI case. So there is again an interpolation. And for each complex iteration, there will be a check on the FSI convergence. And if it's not converged yet, like the displacements and the velocity goes through an FSI solver, I give IS to have a better estimation of the displacements and velocity in the next coupling iteration to achieve the better. All right, the methodology of this case here, of the wiring case, is actually outlined here. So initially we start with a wire which is undeformed. And die diameter, which is expanded with an initial field thickness of 10 micrometers, and the gap between the die and the wire is filled by a soap. So we start the simulation, and actually in the beginning the wire just goes under the die, and we try to find the equilibrium between soap and wire before we start to show you the die. That's due to the fact that we need the electrical stability. Then after 20 time steps, as you can see here, we start to reduce the die diameter in order to achieve that 10% cross-section reduction of the wire. And it needs 1,000 time steps, as you can see here. And for each time step, we need the equilibrium between the loads that are calculated and the displays that are calculated. And at the end, so from 1,020 to 1,200 time step, we keep a constant intended die diameter to reach steady state. All right, the geometry, boundary conditions, and settings. So the soap viscosity is Newtonian, and the constant viscosity is not 50 Pascal seconds. The density is 1 kilogram per meter. That doesn't mean it's air. The fact that we use an incompressible solver, then foam, we have to define it to transfer loads to the structure as well. The density of the wire is 7,800 kilograms per meter. This one has a modulus of 77 gigapascal, constant coefficient of 0.3, yield stress of 1.25 gigapascal, and the parting coefficient of 0.3 gigapascal. A drawing speed of 1.1 meter per second is imposed, and a back force of 100 newtons is applied here. So we have a radius of 0.75 millimeters and a length of 6 millimeters, and here you can see a close-up of the zone of interest. With an inlet also and an outlet and atmospheric pressure. The die has a single angle of 3 degrees. And the orange line represents the FSI interface. And as you can see, the soap is fixed in actual direction, while the wire is moving in actual direction. And that gives some challenges. So that's something we have to deal with. And this one is actually applying the slide interface. So to achieve this one, we need the creation of a new boundary condition, which is recognized as time varying solid interaction boundary condition. What does it do? It's actually imposing the loads achieved from the fluids on the correct position of the actually moving wire. So it has to be refreshed each time step. As we have to deal with plastic deformation, we have a wire due to the conservation of mass has to accelerate. And that acceleration has to be imposed as well on the soap. So that's why we need another boundary condition on the fluid side to achieve the no slip condition. And it's called time varying velocity boundary condition. In order to reduce its computational cost of the whole system, we applied layering because we are not interested in what happens here. What happens here, we are interested in what happens here. So really, when the wire is important. So that's why we applied layering. That means actually in the inlet of the domain, cell layers are added, and in outlets of the domain, the cell layers are removed. So we have some additional settings concerning the numerics. So the total time steps is 1,200. We have a time step size of 5 to the minus 5 seconds and SI tolerance coupling of 5 to the minus 9 meters. This is actually quite strict because we're expecting a film thickness around magnitude over micrometers. Yeah. All right, here you can see the simulation itself. So the die on the decrease its diameter. Here you can see the pressure distribution of the lubricants. This black dot represents actually the moving wire because it's not that clearly visible, but each time the layer is added. Why we have to do that? To avoid detrimental oscillations during coupling. And at a certain point, so the die diameter has reached its final position. We achieved here a steady state calculation. So as you can see, the pressure distribution does not change anymore. So, and yeah, okay, maybe not important. This figure here is 5 times scale in the radial direction. So what do we observe? So we achieved a steady state. as well as so with an interpretation of the sliding FSI interface, so the time varying maximum interaction condition required. We have a no slip condition, can be seen here at this graph here. So the orange line represents the actual velocity of the wiring during the deformation, and the dashed black line represents the coupled actual velocity of the lubricant at the FSI interface. And we achieve a max cross-section reduction of 10%. And as you can see here, maybe not important to mention, you see here very nice that the wire accelerates during this deformation. Okay, so here this slide represents actually how the lubricant behaves during the deformation. So, and that can be expressed in terms of pressure distribution. So here the blue line is actually the pressure distribution of my fluid, and the purple line is actually the shear stress distribution of my design interface, and that can also be defined in terms of wet and Mathieu fluid. So what do we see here in the beginning? We have here a positive pressure pressure gradient, which means actually if we check this one, which is a negative pressure gradient, we should expect a flow that turns back. So indeed, we have here at let's say the boundary with the die, we have such kind of a backflow, something that we expected. So, however, as we see here at the interface of the wire and the lubricant, we have wave flow. So actually here, the shear, we can see it as well here, the shear stress decreases quite significantly. If we check position 2, we see a steeper pressure gradient, so it means actually our backflow becomes stronger. And we have a minimum in shear stress in values, but a maximum in magnitudes. Yeah, as you can see here. What does happens here? So at a certain point, our pressure reaches maximum. So actually our pressure gradient becomes 0. And if our pressure gradient becomes 0, this kind of flow disappears. So we should expect a pure fluid flow. And that's something that happens. So we have here a pure fluid flow. Additionally, we see at this position here, we see that our pressure gradient stays on sign. So becomes negative. And at a certain point, so we have steering on our wedge flow. So the Mathieu effect is superimposed on the wedge flow, and that induces the zero shear stress. And as you can see here, at the FSI interface, just to be clear. So as you can see, it's a very nice illustrated here. At the end, so the pressure gradient decreases significantly, but at a certain extent, it's constant here. So our magnitude of the shear stress increases as well until here. That's due to the fact that we are in an gap. So we get such kind of flow fields. So what are we going to think about this slide? That we have an expected behavior of the flow of the lubricant between the wire and the die, and the shear stress is actually more recorded during the wire dissipation. All right, additional results here. So let me explain first what everything means. So the red line represents actually the die position. The black dotted line here is the U stress at the surface of the wire, and the green line is the equivalent local stress at the surface of the wire. It's a picture of the G2 plasticity, so actually it's like orbital meter stress. So as we can see here, at a certain point, the equivalent local stress is equal to the U stress, and that's the point where the plastic deformation starts to take here. And you can see here as well that the U stress is increasing together with the equivalent Cauchy stress, and it stays after the wire leaves the die, it stays constant. So that means actually from here to here that our wire becomes smaller. What do we see more? So actually here again, the red line is the die position, the blue line is the field thickness of the soap, and the green line here is a radial displacement of the wire. And we see absolutely a very clear radial displacement of the wire, and like a small recovery here. So there's actually more elastic recovery. We see as well a minimum field thickness of around 25 micrometers, and as it's situated at outlet of the die, due to its plastic, the elastic property of the wire. However, this field thickness is too high for dry wire bonding. And that is caused by the most high constant viscosity of the lubricants. So here's some numerical results. So as you can see, we are here at the end of the simulation. So at the steady state area. And each blue dot represents actually a coupling configuration. And we see here that we have more of the whole simulation. We had an average of 4.5 FSI iterations per time step. However, our term Q is equal to 0. But that does not affect at the moment our results concerning the over. So we have to be this result. So what do we conclude? First of all, we have conversion wire having at the side calculation the 10% cross-section reduction in wire. Steady state is reached with coupled velocity between wire and lubricants. Successful implementation of clearing in order to reduce computational costs and a qualitative validation of lubricants behavior in terms of pulse and white flow. And what will be the future work? So as already mentioned, our FINITE is too high, so 5 micrometers. So we have to add piezo-viscous and shifting behavior of the lubricant that will affect. We actually have to go to with pressure and thermal effects, in order to estimate, to have a better estimation of the minimum field thickness. And at the end, of course, it should be validated with experimental data. So thank you all for your attention. So we can get a paper. Any questions?
The thermal is slow, you diffuse very slowly. So might take minutes or hours in real time for the enrichment area. For things the mechanics, it's probably like less a second, which the curve is down. You follow that area to deal with that.
Actually, our purpose is first you we have to shift the effects, compressibility and the case of the student. So if that works fine, then we can be state of the art. Yeah, but then the thermal thing that will be another. So we have still so I have to do some rolling curves and do already aspects not properly, but that's some thermal effects in the lubricant itself. So probably that will be the first. So that's the exact and the big difference in the viscosity. But it comes like yeah, to have yeah, to go a step further on the thermal in the concept of the energy that is.
And for some of the parts that it's not really you're like a sharp point. Is that because of the corner of the sharp?
Yeah, you mean like
so in practice, there's probably some rays there. So
yeah. So actually here,
even delay. Yeah, it's not there. I think it's the last and the final slides. And you're the end of this. Yeah, just see the blue doesn't.
Yeah, here it is.
The silk thickness.
Yeah. And these, so yeah, so actually now it's a very basic now. So normally you should have and we're going to have this.
Any other questions? Yes.
Since we are the certain mechanism in the form, but so you don't know what volume 8 and 1 so 0 in. Could you put everything in one of them?
And yeah, that's actually something in house. But like I use solver, which is written in code, and then for the design, so it's actually an software who is really at the beginning of this developments. So the first wrappers were created were code 8. And that's why like it's a little historical room, so actually I could also use one for and then so that's it's a little historical
If to kind of decipher something, essentially you just have 2 different terminals or 3 terminals. You have a tiny one manager and it would just be run to solvers. And they can get
I can do solve and do functions. The software is and then it's not calculating, so it's calculating the source the rain time.
Yeah.
I think that before you implement the time variant and the service, we will implement the time variant and service
Yeah. So you need the solid traction mount, and yeah. So I think like the solid. So actually, the purpose we can be rich. Like all sides, the loads and the other sides, like the velocity. So that's why so the basic of the time varying mass splits the traction calculation is the time varying mass fixed time images which you can find in OpenFOAM itself. And the solid traction calculation also you can find in the source code. So actually those two calculations merging each other gives the results that we want to use.
I think it's in convergence when you implement the variant and sort of this. So I think the convergence that when you implement the time variant,
it's really solve the problem. It's not to be a convergence because like if I remember well, the solid traction it's not updated each time step, but it's a little bit it's really so we are implementing a lot of it's like like yeah.
Because one asking is because I feel like Singapore then you have a problem appearance of the solution.
Yeah.
And the way I actually defined by one of the conditions mentioned, there was a middle line and the time series. So you have just one line and four every time.
Yeah, so maybe allocate them. So I refresh each time my files. So I could refresh and refresh files for each iterated, not even each time, but each iterated is a refresh with the data that I actually from the tools. Yeah, so yeah,
Let's make another
Hello, my name is Patrick Höhn. I'm today representing two universities because when I was submitting it, I was a PhD student and working at Lausanne University of Technology. And today I'm an employee of University of Göttingen. So today I'm talking as a representative of two universities. Basically, my talk today will not have much of result compared to the last talk, but it's more or less learned what I have seen in my PhD work in the last 5 years when working with OpenFOAM. For the outline of the talk, at first I will talk a little bit about the application area from which everything was motivated, and then I will talk about the different design iterations for the solver I wanted to develop, how they went, and now summarizing what I did in the last 4 years. How I would do it now with the knowledge I have now if I had to start again. And I believe if I want to make the code sustainable and upscale it, I will also partially do I have to do the work again. With that, I would like to slowly introduce the application area is drilling engineering. So drilling for oil, gas, or more recently, geothermal energy to also capture either H2, hydrogen, or carbon dioxide in the ground. And when I did start the work, it was mostly about geothermal energy in our institute. So there, the costs are higher compared or similar compared to oil and gas, but the risk of being successful and having a plant is much higher. Also, the return of investment is lower. So if one wants to get geothermal energy, one really needs to reduce the cost. And there, the largest cost driver is non-productive time. So when we still have the rig rented, but we cannot build because something is broken, we need to do some maintenance or something happens which we did not expect. And that is mostly related to the vibration of the drill string, and also to non-optimal catalyst approach. which already brings me to the two things I wanted to combine, which was also my title, the tilting vibration, which is the fluid structure interaction, the FSI problem, and the cutting support, which is the particle transport issue. And what I'm talking about today is just simulation-based approach with OpenFOAM, because in a real industrial field application, you generally don't get the data and also not with the time resolution that you would like to have. So what is causing those vibrations? There are quite a few. For torsional, that can be the drilling action with a top drive propelling it, or the mud motor, but I won't talk much about that today because I'm into lateral vibration, and that is governed by buckling, wall contact, and more importantly for me, for the drilling fluid flow and for cutting beds. And here you can imagine how such a cutting bed would look like. So here we have our inner drill string, and here we have the particles of the cutting. Just here the picture is of course ideal because the particles are spheres, which of course you don't have in reality, but for the computation, you generally use it because it's the easiest way to at first get some work done in that area. With that, I just would like to briefly show my simulation setup. So basically, I just cut off the drilling string and just take a very short section. I keep the important elements to study the damping of the lateral vibration. I fix one end, the other one I induce vibration by some sort. In experiments, it was a little bit different, but still. And then in the animals, I have my flow and particles. And in the experiments, I also had a rotation, but I will consider that in my simulation. That would be something to do with the future. And that up, I wanted to simulate with OpenFOAM. That was my dream, my vision 5 years ago, in 2018. So then I thought, okay, what software could I use? For the particle tracking, actually the choice was quite a couple of choices, but my choice was pretty quick. There's, for example, CFDM coupling based on light, steady-foam based on length, where one can mention light with a macro scale form of length, so to speak, and then of course OpenFOAM determined volume. Because in the institute we used the first one already, so was a big choice, and stick with that one. For the fluid-solid interaction, there I was adventuring more. At first, I started with an FSI toolbox from the extend cluster. Then, after 1 year, because it's no longer maintained, and there's a successor, SolidFOAM, I was switching over to that. And now, looking back, I would switch again over to Precise. And of course, besides, there are also OpenFOAM internal solvers, which I did not consider. But so basically, I'm moving all the way from top to bottom into here, and also for the future. So that was my first idea. I just used the FSI library, which is based on foam extent. And unfortunately, the CFDM company was not based on extent, but on formation. So that already gave me then the question, so what am I porting, FSI or CFDM company? In the end, I decided to port CFDM company over to foam extent. And then, with the interaction which I need for my simulation problem by two types of communication. First, light, of course, needs to communicate with solid solver to allow the impact, to model the impact of the particles on the inner pipe. And of course, I also have the need to have the fluid coupling. With that, I had some challenges with that. First, of course, the porting of the code. No fluid solver at that point had any particle effect included, so I had to include that. Light was also not completely treated, and the communication scheme which was there, so I also had to add only measurable lights, which wanted there in the public version, and also to couple the mesh changes and the forces that would between the lights and the solution versus also so quite a lot of work. But yeah, then I got to know, yeah, the toolbox is no longer maintained. I couldn't maintain it. Not the nice idea. So then, it's the next year, I decided to switch over to FLUID-STRUCTUREINTERACTION and start porting all my code over to FLUID-STRUCTUREINTERACTION. And you see one more, but at least I did not need to do the porting to extend again. And I simplified my setup also a bit in a way that I just pushed now all the forces and the mesh movement via the solid fluid solver so that the solid solver can remain unmodified. But yet there were still some more challenges. Also, the first point I mentioned, the second one, lights and CFD uncoupling also, at least with the public version, have severe scaling issues. If you go to more than 15 cores, your performance, you have a very fast performance drop, and it does not scale out at all. It's a design limitation of the public version, so that is something to overcome. Another thing which is, of course, tricky, the particle solver generally runs at much smaller time steps, maybe at the difference of 10 to 100, compared to the fluid. And also the solid, of course, which means unless I have a coupling scheme, I need to run everything at the particle time step, which is computationally very, very fast. And that's something which I did not resolve actually yet. And also, if you want to go to training application, you also actually would need viscoplastic fluid, because the training fluid generally is viscoplastic. Something which I try to implement some courses which extended I think 2 years ago. So with all of that, how should the future look like in my opinion? Basically, I already mentioned a bit that upscaling code and changes and maintaining can be really painful. And that is also valid actually for CFD uncoupling and lights. The public version of CFD uncoupling is not maintained in many years, but luckily there's an academic fork, the PFM version, which is actively developed. So basically for my new setup, I also have to start porting again from the public version over to the PFM version. And if I'm already doing that, why not make my setup a bit more flexible? And this is where I got inspired by Philip's interface to precise, so that you can use the solid solver, also in precise from FLUID-STRUCTUREINTERACTION, and then I should also maybe couple the PFDM coupling and OpenFOAM via precise to the solid solver, which does not need to be FLUID-STRUCTUREINTERACTION, could be also something else. But it of course means that I need to make a new precise adapter, considering the particle. And one advantage will be for me also that I can switch better between OpenFOAM version, because precise supports not only one version, and developing against many versions will also maintainability not really so nice. So I hope with that approach I get more flexibility. Hopefully also my modifications I can better upscale it to the PFM fork. Hopefully also to precise, and then that way after I finish the work in that area, I can use it, because I believe sustainability is only forward is a difficult thing. If you finish your PhD, open your code, yeah, it just stays how it is, and it's no longer maintained. So I have got the hope that maintainability and also flexibility increases. I have for that generation another idea, but I'm not sure if it is a good way to do. That would be just also cut away here the lights and couple it directly with precise. But I'm a bit afraid that many of the things which are in the CFDM coupling, I need to re-implement in the form lights to precise. I'm not sure which of the two approaches should be then the way to go. With that, I would like to slowly conclude my talk. For in the last year, I have been maintaining code and also keeping up with upstream can be very challenging. So I believe it's a good approach to also make the code in a way that upstream projects can use it. Hopefully also they are willing to accept the modification and maintain it. And it's very important to carefully choose the approach, but it can still happen that some software becomes unmaintained when you're working on things. And yeah, any of those changes, I don't mention because it's extremely time consuming. And now for the future, I need to see which of the last two approaches I should use, then implement it. And since I'm now in Göttingen, I'm also, my research might also shift a little, where I would maybe look more on OpenFOAM IO, because I'm more in an IO project. And also I'm curious to see what will happen with GPU computing in OpenFOAM, because also the AWS talk we heard, that can be a good thing for the future, so I'm curious to explore that. And with that, I would like to still thank the person of the agency funded network, which was the German Federal Ministry for Economic Affairs and Climate Action, the Northern German Supercomputing Alliance, the computing power, and also the Simulation Science Center, Cluster Göttingen, also partially funded the work. And then I would want to thank you for attending my talk. I hope now we have any questions.
Thank you very much. Any question? Yeah, I have a couple of questions. Oh, yeah. Very good. Sorry. There's nice.
Yeah.
So, from your perspective, what do you think would be trying why do they want to speak that? It's essentially very broad interface.
Yeah, I mean, it's more or less where I draw the interface from lights, because the calculates I omitted in the next slide. And yeah, it's just a question, where do I introduce my particle effect? Do I use the existing library, or am I coupling it directly to precise? So that's more the question which I
think it would be more helpful if instead of drawing this you very broad domains try to identify interfaces where you need to compute. Because if so interface is completely isolated from the fluid particles, then from this it's better to keep lights basically. Provided that this is not complete with the aspect.
I mean, basically, all the domains are interconnected with each other, all interact.
Okay, then maybe something like usual here, that not makes the most. Even if you need to work something, how much you need to, how much work, how much really nice.
I don't know yet. Maybe I can report next year.
Have you considered the particle modeling options? So I haven't used it as the solver tree particles.
I have not considered that much. The background was just when I started my PhD. We had a postdoc there who started who did his PhD with light, so it was more, I would say, historically formed that I decided to do that.
It's quite a software challenge. There is some physics challenge, but it seems that you're putting most of your energy on software. So
yeah, software design. It is more software design defined things.
Hi, good afternoon everyone. My name is Seevani Bali. I am a PhD student in University College Dublin. Today I'll be talking to you about frictional contact interactions in beam theories, which is implemented in a finite volume framework. Beam or rod theories are continuum formulations which are used for modeling slender rods. There are a variety of applications for such slender rods, starting from biomedical applications. We also have human hair, mechanics of human hair, which are modeled using such theories. We can also model any wires or cable assemblies in vehicular structures or soft robotic arms using such beam theories. And knot mechanics, flexible rods, even like flexible roots and root modeling or DNA modeling, biopolymers, textiles. These all are examples of such engineering or applications where beam theories are necessary. An FSI application of slender rods is mooring lines, where we have cable dynamics and floating bodies interacting with the cables. With respect to OpenFOAM, cable dynamic modules available for coupling are MUDI and MUDINE. These are generally finite element and lumped mass models. An alternative to that could be a beamform formulation, which we have implemented. The beam formulation is implemented currently in finite volume formulation for cables, and my another colleague Amir Hussain is extending it to the FSI coupling. If you're interested, please feel free to look into his presentation. Coming to the beam solver, a beam is generally a term used for slender structures whose length is much greater than the cross-sectional area. These theories are generally one-dimensional in nature. And the SIMO-REISSNER beam theory is a specialized beam theory which is geometrically nonlinear, so it can handle large displacements and large rotations, but the strains are small because we are assuming linear elastic models, material models, and these theories can model axial forces, shear forces, bending moments, torsional moments, twisting, and all such motions of slender structures, and hence they are quite powerful. The governing equations of the beam solver, the differential form is the linear momentum equation is this. The linear momentum equations are in the forces per unit length format. Hence, in the integral form, which we use in finite volume formulation, we have length integrals instead of volume integrals that you see generally in solid finite volume equations. We also have an angular momentum equation because this beam theory solves for displacements and rotations, and these rotations are non-linear. So you see the lambda here, they are large rotations, and hence it's a non-linear formulation. So we have angular momentum and linear momentum. The discretized equations is basically balance of forces and moments across the internal faces. So the equations that we saw in the previous slide, the forces can be discretized as forces in the east face minus forces in the west face. Similarly, the moments also can be discretized as moments in the east face minus moments in the west face. We also have some coupling terms, and which are modeled using discretized using trapezoidal rules. And also we are using a cell-centered finite volume method, and the gradients are we are using an orthogonal gradient scheme and linear interpolation to interpolate cell centers, values at cell centers to the face centers. Okay, as I said, these coupled equations, the linear and angular momentum equations, they are non-linear because of the nature and the geometric non-linearity of the problem, and hence we are assuming we are adopting for an implicit solution. The discretized system of equations look in that format: A delta phi is equal to R, where delta phi is delta W and delta psi, where these are the correction of displacements and correction of rotation vectors. We are using a Newton-Raphson algorithm, which basically says that take the derivative of the polynomial functions, which is the linear and angular momentum equations, with respect to the current state of variables, primary variables, displacements and rotations, multiply that with the corrections, and the right term is the source terms. So once we find out these corrections, the delta phi terms, this is how we upgrade it. You can also see here that the upgradation of a rotation matrix is not straightforward, it's a nonlinear map. Okay, coming to beam contact interactions, whenever there are more than one slender rods interacting with each other, a contact formulation is also necessary, which is also implemented in this beam solver. For large contact angles, meaning imagine two pens which are intersecting at an angle greater than 30 degrees, between 30 to 90, we can imagine that the contact is happening at a single point, and hence we assume it to be a point-to-point contact. When the beams are almost parallel, then there can be multiple points of contact, and then we call it as a line-to-line contact formulation. So these are the two contact formulations that we have in beams. When I say a line or point, the contact detection is actually happening on the beam center lines. So the solver does not really know the beam surface. So it's always detecting the points on the center lines. Coming to point-to-point contact, here we have two beams. Basically, when we are detecting point contact, we are trying to find the minimum distance, which satisfies two orthogonality conditions. So the distance, the minimum shortest distance, is orthogonal to the tangent vector at the contact point on the first beam, and also at the contact point on the second beam. So we have two orthogonal equations and two unknowns, and that's how we solve. And these equations are nonlinear. We use some procedures to solve these equations. Once the points are known, we establish a gap function, which is basically the difference of the position vectors of these, magnitude of the position vectors of these points, minus R1, R2, which is the radius of the circular beams. So here I'm assuming that the beams are circular in nature, and hence we can assume that, hence we can establish kind of the center line contact being transferred to the surface contact of the beam, so to say. So having established the gap function, if the gap function is less than 0, means the beams are penetrating, then we have a contact force, which is given by a penalty law, where Pn is the penalty stiffness and Gn is the amount of penetration occurring, and D is the unit distance along the same direction, the minimum shortest distance, and otherwise the contact force is at 0. One such application of frictionless point contact is building a 5x5 net, as you can see here. So at the start of the simulation, the beams, you have 5 beams which are completely perpendicular to each other and not interacting. And as the time progresses, the beams form a pattern such that they make a net-like formation. And you can see that we have 4 configurations, and at the end of the time, all the 5 beams are successfully forming a net. So this is a benchmark test case for point contact, frictionless case. Now if you want to add the frictional effects to the beam contact, I'm using a Coulomb friction law and a stick-slip analogy of plasticity. Here the assumption is that the frictional forces that are acting on the beam surface is actually transferred to the center line, assuming negligible frictional moments, and that's assumed because we're assuming that the beam cross sections are small. So imagine that the beam in the beam center line we have a point of contact and at the location blue, and if there was no friction, in the next time step the point would move or slide to the location given by yellow, and the total amount of displacement or tangential motion that the point would undergo is given by GTI. Now if there was friction, a part of that motion is being restricted by the frictional force, and only when the frictional force is surpassed, then the red point slips off to some other location. And the amount of sticking, let's say, which leads to the contribution of frictional force is given by GTEI. Now if we encapsulate this concept in an equation, we can have this equation right here, where the total tangential gap, GTI, which is the sliding of the contact point along the beam center line, can be divided into the GTEI, the elastic gap, which contributes to the friction force, and GTPI, which is the plastic gap, which contributes to the slipping of the beam of the contact point. Now, in order to calculate how much friction force or how much sticking has happened, we can calculate how much slipping actually happened and back calculate the sticking gap. So the slip increment rate used here is given by this formula right here, with the dot product over on the top of GT and zeta is the time derivative, and the flow function here Fi is given by this flow function right here. Now if we differentiate the flow function and use an implicit backward Euler scheme, where we'll arrive at this formula. And as you can see here, it says that the plastic gap in the new time is equal to the plastic gap in the current time, the old time, times some delta t in the delta xi in the delta t increment, multiplied by the sine. This sine of the NTI, which is the frictional force itself in the new time, the sine of this quantity decides the direction of motion or the direction of sliding of the two beams. So as you can see that we have two unknowns and both the sides of the equation, LHS and RHS, and hence we need to fall back to some trial solution first. So the trial value over here for the frictional force is NT. Trial value of frictional force NTI is given by penalty stiffness. Again, we are using a penalty law, multiplied by the tangential gap, which is known for a particular position of the beams, because we can actually track the position of the contact points by the position vector of the contact points and the previous slipping gap or the slip gap in the previous time step. So this trial value is substituted in the flow function and we get the stick slip condition. So if the Fi trial is less than 0, that means it falls in this region, the red region of the friction force. That means the friction force has not surpassed the maximum allowable friction given by mu nc, where mu is the coefficient of friction and n is the normal contribution of contact. And since it hasn't surpassed, the beam will stick and the slipping is 0. So delta zeta I is 0. If in fact the trial version is greater than or equal to 0, that means it has surpassed the maximum allowable friction, and then we restrict the total frictional force to mu nc. That's the maximum allowable friction, and we can calculate the plastic increment, the slip increment. Finally, we can, using this value, we can back calculate the sticking displacements. So these formulae are used to model the frictional contact. Coming to an example, here we have two perpendicular beams, and so we have beam 1 and beam 2, and the normal friction, the normal penalty stiffness parameters and the tangential penalty stiffness parameters are given, the radius of the beam and the control volumes, the number of discretization. Here is the wireframe of it. So the amount of displacement applied is right here. On the beam 2, we are applying a displacement of 4 meters because the beams are in meters, 4 meters in the x direction and a displacement of 1 meter in the negative z direction. So if there was no friction, we would see the following. So if for a frictionless case, since the beam was moved 4 meters in the x direction, so the entire beam essentially simply slides off, and we can see that the Wx, or the displacement in the x direction, is 4 meters, and the red, it's all red throughout. So there is simply sliding motion. Similarly, the z displacement is -1 in the location because we have pushed it down, and some amount on the opposite direction. Now, if there is friction, which is this case, friction with mu is equal to 0.6, the picture over here clearly shows that the displacements at this right end of the beam is inhibited. Now it's all not all red. So there is a restriction of the motion due to the addition of friction. Similarly, the displacements in the z direction, even so it's -1 here, which we provided the displacements, but on the other end it's for the frictionless case, it was 0.98. Now it's 0.70. So there is some inhibition of motion due to addition of friction. So if we see the final graph with no friction, mu is equal to 0, the beam is simply sliding. But with mu is equal to 0.6, there is an inhibition of the motion, and that's the overlay of the two final deformations. Now, if we try to plot the graphs of the elastic gap and the plastic gap, and here I'll remind you that the elastic gap contributes to the frictional force. So the graph on the left is the elastic gap of the first beam, where the beam is being pushed on the right. And for mu is equal to 0, simply there is no elastic gap. It doesn't contribute to any friction force. On the other hand, the plastic gap, if you see the green graph, it reaches to near about 4. So we push the beam by 4 meters. So we can see almost that the entire motion being converted into the sliding gap. Now, as you increase the frictional coefficient, you see the increase in the nonlinear increase in the elastic gap, and you see the decrease in the plastic gap because it's slipping less and less due to increasing friction. So these are one of the few graphs for the beam. Now, coming to some of the convergence issues of the solver, especially when there is a large sliding case and in the sticking phase of the large sliding, because the beams are moving quite fast. Even for smaller time steps, it's not able to converge. The convergence is a problematic criterion here. So a naive way of solving this problem is by under relaxation. So where I'm saying that, okay, the frictional contact force that is because I'm using an implicit method, iterative scheme, the frictional contact force in the new iteration is equal to the frictional contact force in the previous iteration plus some under relaxation factor times the predicted value that we actually predicted from that iteration, and I'm trying to under relax it by some factor, and this under relaxation has resulted in convergence of certain time steps. But even with the under relaxation, there are some small time steps where the residuals are found to decrease but not completely fall below the tolerance level, leading to maximum number of iterations. So this is one of the problems that I have to consider in the future work. So just to show you an example of where such problems are occurring, and you have 3 beams where the beam on the first, showing by my slider over here, that is being pushed up. So due to the domino effect, all the other beams are being pushed up. So a frictionless beam would look like, okay, the beams are moving, and you can see that there is a lot of sliding happening and a lot of contact happening, and for frictionless case, so that's a large sliding problem. So final motion is this. Now, when the friction is considered, I think the frictional value is 0.478 or something, you can see that, okay, just let's wait for a second. You can see that there is a slight jittery motion over here. So it's sticking and slipping. So there are some numerical divergence issues for this problem. I did try to reduce the under relaxation factor, but there are still some problems which has to be considered in my future work. That's all there is to this presentation. Thank you for your questions, and thank you for your patience, and please feel free to ask me questions.
Bali, are you there? Can you hear us?
Yeah, I can hear you. Can you guys hear me?
Yes. The volume is very low on the video.
Yeah.
Okay, do we have any questions here? We have time for maybe one short question or a little bit over. No? Okay, I can ask you a quick question. Shivani, if you can hear me. And what resolve the problems with the jittering in the contact? Do you have any ideas how you fix that?
So Yes, I think so. The under relaxation helped a bit, but I was trying to, when I was trying to do the implicit corrections to the friction, that I dropped out certain terms due to some convergence issues. But I think that if I add those terms, there is some problem with the implicit correction terms, is what I feel. Maybe if I change them, there will be a better convergence. Also, I think it's a large sliding problem. It's slightly dependent on the mesh, and that's why this problem is not really exactly clear what's happening behind the frictional, the jittering phase. But I think I'll look into it more. Mostly it's because of the implicit corrections, is what I reckon.